Hello everybody and welcome to the lesson number 7. The name of this lesson is Pumps versus System Curve. In the past lesson we have learned how to determine the pressure losses and the head losses for a straight pipe and for fittings and accessories of piping. Knowing this, we are ready to calculate the curve of the system. Let's see here some examples of calculation of this curve, and also we will see how this curve of the system match or cut the pump curve. So let's start with this lesson. We have represented here a drawing or scheme similar to the one that we have seen in the past lesson, where we have to convey a fluid from the section 1 of a pipe with determined operating conditions to the section 2 with other operation conditions. The head at point 1 is the sum of the three terms of this equation as we have seen before, and the same at section 2. What is the energy? What is the amount of energy that we need? Only this difference between H2 and H1? No, we need to add another term, the pressure losses, to cover the losses of energy that we will have when transporting this fluid. So, the energy that we will require to convey this fluid from point 1 to point 2 by using a pump, the energy that is required by the system is equal to the difference between the head or the energy at point 2 minus the head at point 1 plus the pressure losses. Let's rearrange the equation to focus on the part of the equation, of the part of the energy that changes with flow rate or with velocity, and the other one that doesn't change. So the head required by the system, or the head that the pump should add to the system, is equal to the difference between the geodetic heads plus the difference between the pressure heads between the point 2 and point 1 plus the difference on velocity head between these 2 points plus the pressure losses. So the static part of this equation is composed of the difference in geodetic head plus the difference of pressure head. This static head doesn't change with the flow rate, doesn't change with velocity. That's why we are calling this static. On the other hand, the other part of the equation is the dynamic part of the equation. The part of the equation, of the terms of the equation that do change with velocity, that do change with flow rate. These terms are the velocity head and the head losses. Both, of course, change with the flow rate or with velocity, of course. From a practical point of view, this term, the velocity head, the kinetic energy, can be neglected. It is very, very small value, close to 0. It is not significant, so we can neglect. If you want to calculate more accurately the head, you cannot. If you want, you don't need to do this. You cannot neglect this, but in practice, it doesn't have any great influence on the final value of the head, since the value of the when dealing with pumps, But anyway, if you want to add or to consider this term, please do it. But in practice, it is not necessary. So if we do this, then the result is the one that you are seeing in this equation, the equation 4, that the energy or the head required by the system, the head that the pump should add to the system, is equal to the static part of the head, the difference in geodetic head plus the pressure head difference, or the pressure head plus the pressure or head losses. Now we're going to see how to calculate, how to draw, how to build the curve of the system for different cases that we will see now. The first of these cases is this one. We need to transport or to convey the fluid from one vessel to another. The atmospheric pressure is acting over the liquid surfaces of both vessels. We will take we'll pass the reference plane through the pump suction or the pump impeller. Here we will have the datum plane, the NP shape plane. We will select the liquid surface as the section we will analyze, section 1 and section 2, with the difference in head, geodetic head or height, delta Z 1.1.2. So we have here the equation that we have seen before. This term can be eliminated because the atmospheric pressure is acting on both sections 1 and 2. Another thing, and very important, if we have selected the liquid surface as the section, at the reference section, since the fluid is in static conditions or doesn't move at fluid surface, we can consider that velocity at both liquid surfaces at section 1 and section 2 is equal to 0. So the equation remains as you see here. The required head by the system, or the head that the pump should add to the system, is equal to the positive differences in this case between both sections 1 and 2 of geodetic head plus the energy losses. The geodetic head difference is the static part of the equation, and dynamic part of the equation if the one referred to term the head losses. And we see here the head losses are equal to a coefficient multiplied by a square flow rate or a square velocity. Can be directly determined through this equation. I will remark again, the static part of the equation doesn't change with the flow rate or with velocity, and the dynamic part of the equation does change with velocity and with flow rate. Let's represent now this in a curve. Let's represent, the curve of the system. We are drawing here the static head, and in this case, where the atmospheric pressure is acting in both sections over the liquid surface, we have that this static head will be equal or equals delta Z. And this value of a static head doesn't change with the flow rate. We can draw the system curve. Why this curve has this shape? Because what we are adding to this curve is the dynamic part of the head that change with the flow rate, with the square flow rate. So we have this quadratic equation. In this case, we have two vessels under pressure, P1 and P2. This could be, for example, P1, the vessel 1, the aerator in a feed water pump, in a feed water system or the power plant, and we have to convey the feed water from the deaerator to the, for example, to the boiler drum. So we will have a low pressure P1 on the aerator, and we will have a very, very high pressure P2 on the boiler drum. The same as before, let's establish the datum plane here, and the sections will be located also over the liquid surface in order to eliminate the term velocity head. This is the difference in geodetic head, although of course the more important term here, the term that has more influence, more impact on the required head by the system will be the static pressure rather than the geodetic head, especially in the case I mentioned before. We have the equation here. We can delete or remove the velocity from the equation because we have selected that the sections are located over the liquid surface where velocity is 0. So now we have this equation. Not only the geodetic head is the part of the static head, but also the pressure head. So the static head will remain this way. This is the shape of the equation, while the dynamic head will be the same as we have seen before and will vary with the square flow rate or square velocity. Let's represent this in the curve, the system curve. Now the static head will incorporate the turn pressure head, will not change, will remain the same although the flow rate will change, and the system curve will be the one that you are seeing here. We have to add the dynamic part of the head, the part of the head that does change with the flow rate. Now we are seeing a system acting by gravity, a system by gravity. We have here two vessels. The atmospheric pressure is acting over the surfaces of both vessels, over the free surfaces of liquid. The vessel 1, the free surface of the vessel of the liquid of vessel 1 is above the free surface of the liquid 2, so we can convey the liquid from vessel 1 to vessel 2 in principle by gravity, due to the gravity force. The difference between the section 1 and section 2 is the one we have represented here, and the reference plane will pass through the section 2 to eliminate this term of the equation. We will see now. We have the equation we have seen before, of course. We can delete the term Z2 because it can be considered 0, considering as reference the reference plane we have drawn in this drawing. The difference in pressure will be also eliminated because the atmospheric pressure is acting on both liquid surfaces, free liquid surfaces, and velocity can also delete it because we have selected the section at matching the free surfaces of liquids. So the equation that results from this is the one that we are seeing. The energy required by the system to convey the fluid from the point 1 to the point 2 by gravity is equal to minus Z1. We have a negative geoelectric head. That means that this geoelectric head is helping us to convey the fluid from the vessel 1 to the vessel 2. This is the action of gravity. That's the meaning of the sign minus here. So the static head will be negative minus Z1, and the dynamic head the same as we have seen before. So let's see that the axes are a little bit different. Why? Because the static head now is negative, now it's below zero, because gravity is helping us. It doesn't change with the flow rate, and we can draw the system curve by adding the dynamic part of the head, as we have done before. And what does point mean? Well, this is the flow rate that we can deliver, or that this system can deliver by gravity. Let's see now how the pump acts in front or versus the system curve. We have the curve of a pump here represented, and this is the system curve of a system we have named system 1. What is the meaning of this point? This is the point in which the pump will operate. At this point, the pump will deliver a flow rate Q1 and head H1. Of course, as we have seen before, this is the system 1 is obtained by adding the static head Est1 plus the dynamic head, the head losses. Let's suppose we want to reduce the flow rate. Then we can close a valve, for example, a valve located in the pipe or in the system. And what we are doing is throttling the system, increasing the pressure losses. How would react the pump? Of course, this pump will deliver a lower flow rate at a higher head, at a higher pressure. Why? Because the curve has changed. And how the curve has changed? This way, now we will have this new operating point with the flow rate Q2 and a head H2. Of course, this curve has been obtained the same as before, of the sum of the static head 2, that is the same than the one of the system 1, plus the pressure losses HL2 that are higher than the previous pressure losses because the throttling effect of the valve we have closed in the system. Now let's change the static head and let's see what happens. Now the curve is the one of the system 3. The operating point will be this, a higher head H3 and a lower flow rate. We have increased the static head. And due to this, how the pump has reacted, reducing the flow rate and increasing the head. Of course, this curve has been obtained by adding also the pressure or the head losses to the static head. Well, this is all for today. I will be waiting for you in the next lesson. Bye bye, ciao. Arrivederci. Adios.